Let us derive an equation for the electric potential due to electric dipole on its axis, any point on its axis. You can take down this question, deduce an expression for the electric potential due to an electric dipole at any point on its axis. Deduce an expression for the electric potential due to an electric dipole at any point on its axis. We'll try to deduce this equation. Now consider an electric dipole plus q and minus q. Consider a dipole minus q and plus q. Let us say O is the midpoint, and we can mark these 2 points also. This is A, this is B, and we know the distance between two dipole is 2a. So from midpoint to A it is A. Similarly, from midpoint to point B is also the distance is A. Let us say we have to find out electric potential at any point on its axis. So we will take another point P where we have to find out the potential on its axis. Consider a point P which is lying at a distance r from the center O, and we have to find out potential at point R. Let electric potential to be obtained at point P lying on the axis of dipole at a distance r from the center of dipole. Let electric potential to be obtained at point P lying on the axis of dipole at a distance r from the center of dipole. We know by superposition theorem the potential at point P is the sum of the potential due to minus q and plus q. Electric potential at P due to plus q and minus q charges is the due to plus q and minus q is obtained by using principle of superposition. Is obtained by applying superposition theorem. So superposition of electric potential. So total electric potential at point P, V is equal to potential due to minus Q charge, potential due to minus Q plus potential due to plus Q charge. Potential due to minus Q charge is 1 by 4 pi epsilon naught into minus Q divided by distance of minus Q from point P, that is R plus A. Plus 1 by 4 pi epsilon naught into Q divided by distance between B and P, that is R minus A. Now you simplify this equation, we will get the potential at point P. P is the axis of the dipole. Take out 1 by 4 pi epsilon naught outside because it is common. So 1 by 4 pi epsilon naught into, you can take Q also outside, 1 divided by R minus A minus 1 by R plus A. First I wrote 1 by R minus A, then this is minus sign, so I wrote it next. Now take the common denominator and simplify. Q divided by 4 pi epsilon naught into R plus A minus R minus A divided by R minus A into R plus A, that is R minus A into R plus A. Q divided by pi epsilon naught into, here R will get cancelled, A plus A, so that will become 2A plus 2A divided by R square minus A square. And we know for a dipole moment is given by P is equal to Q into 2A. So replace Q into 2A by P. We'll get V is equal to 1 by 4 pi epsilon naught into P divided by R square minus A square. Where P is Q into 2A. And if the point P is very far from the dipole, or if A is very less than compared to R, then the potential becomes equal to 1 by 4 pi epsilon naught into P by R square. This is the potential at point P, and if point P is far away from the dipole, then V is 1 by 4 pi epsilon naught into P by R square. We can say from this equation V is inversely proportional to R square. So potential due to dipole obey the inverse square law. V is proportional to 1 by R square. Whereas if you see the potential due to a point charge, it is 1 by R. So see the difference. Potential due to a point charge is inversely proportional to R. whereas the potential due to a dipole is inversely proportional to square of the distance. V is proportional to 1 by r square. So sometime they may ask you, like, show that the potential due to a dipole on its axis is inversely proportional to square of the distance r. So you can do this derivation in that case. When we take the potential V due to dipole at large distance from the dipole is, we get the dipole, the potential due to dipole at a large distance varies as square of the distance, inversely as the square of